Cannot connect to the audio speaker setting. So the homework still due Monday. You can either submit it to Professor Pauline Yadak, the physics lady in the physics room in the STEM Center, or you can drop it off in my office in 18109, or you can submit it online as well. Okay. The lecture is not going to happen at 11 a.m. It's going to happen at 5 p.m. At night. So it's going to be, if you want to listen, it will be online. Okay? Let me see. Share my desktop. Let's make sure that I'm ready. Did you all get that? So you don't have to come Monday at 11. If you want to listen to the lecture, I'll be in Minnesota doing the lecture. Okay? Let's see. Let's try and finish work energy. There's just one more example left. So that means we're only about 3 slides behind. So we're going to try and catch up today. We've looked at the case of motion of an object that is under the action of a conservative central force, right? We looked at it from the point of view of conservation of angular momentum, right? Small h, angular momentum about the point where the force passes through all the time is conserved, right? So under this scenario, if we assume, for instance, here's the Earth and there's a satellite, okay? At any position of the satellite, we know that what? The force, the only net force acting on it is the gravitational force. The pull of the Earth on the satellite, it always passes through point O, which is the center mass of the Earth. Therefore, it's under it's under conservative central force because number one, it's a central force because the force always passes through the same point, and number two, the force of gravity is also conservative, right? So for such a case, not only do we know that the angular momentum about point O should be conserved, right? This is a statement of the conservation of angular momentum, right? Angular momentum is what? It's the cross product between the position vector from point O to the satellite and the linear momentum mv, right? So it becomes like this, r naught mv naught sine phi naught is a constant, where phi, of course, is the angle between what? The position vector r and the velocity vector of the particle, okay? So not only is the angular momentum conserved about point O, since the force of gravitation is also a conservative force, so the total mechanical energy is also conserved. So initial kinetic energy plus final plus initial potential energy due to gravity is equal to the final kinetic energy plus the final potential energy. And initial kinetic energy is of course 1 of mv naught squared. Okay, and if you remember, right, potential energy due to gravitation is negative g, mass of the Earth, m divided by r naught, which is the distance between the satellite and the Earth. So we can apply these two equations simultaneously to solve a problem that we were not able to solve previously. Okay, we'll revisit that problem. So if we know the distance that we're interested in, okay, we can solve these two equations 1 and 2 for the other two unknowns, v, which is the speed of the satellite, and c, the angle between the two, okay, the position vector and the velocity vector. Okay, of course, at the positions where r is either a minimum or a maximum, okay, the angle c is 90 degrees. Right, we were able to solve a problem last time, if you guys remember, a satellite being launched, right? Only because the problem states that we're interested in the position or the velocity at the farthest point, and the position of the farthest point was given. In fact, with this additional equation coming from conservation of energy, we don't really need to know where that maximum distances. So here's an example. Very similar to the one that we did before. Okay, a satellite is launched in the direction parallel to the surface of the Earth with a velocity of 36,900 kilometers per hour from an altitude of 500 kilometers. Okay, so it looks like this point of launch of the satellite is the perigee of the satellite. That's the position where it's closest to the center of the Earth. Okay, and then we're asked to find, letter A, the maximum altitude reached by the satellite. Okay, and letter B, the position of the satellite when its speed is 35,000 kilometers per hour. Take note, just for reference, let's compare this with, I don't know if I can find it. I can guess that it's about, oh, it's in a different PowerPoint file. So we solved a problem very similar to this last time, right? However, in that problem, I actually specified how far that maximum altitude is, and I asked you to find the velocity there, right? Okay, with our knowledge of conservation of energy, we don't need to know either where that maximum altitude is or what the velocity is at the maximum altitude. We can find those two by combining our knowledge of conservation of angular momentum about the center mass of the Earth and conservation of total mechanical energy. So let's do that. Oops. So we are given, okay, I'm going to call this position A, right? And the maximum, the position corresponding to the maximum altitude as B. So we are given what? The distance from point O to the satellite at the initial position is, how much is that? It's the radius of the Earth, right? Plus 500 kilometers. Now, what's the radius of the Earth? This is in kilometers rather than. Anyone with a guess? Just a guess. Order of magnitude. Anyone? Is it billions of kilometers? Okay. Oh, it's that 6,371, 78. Okay, 78 is actually the equatorial radius of the Earth, because we know that the Earth is not really a sphere, right? It's actually an oblate spheroid or an ellipsoid. It's actually fatter at the equator compared to the poles, right? Why is that? Why is it, instead of being a perfect sphere, it's kind of like this? Not really. Why is that? It's so the equatorial radius R sub E is the 6378. The average radius is around 6371 kilometers. But why is it flatter on the poles and fatter around the equator? Oh, because of the rotation, right? Okay, because of centrifugal force, quote unquote, right? Since the Earth is not really perfectly rigid, some of its mass tends to be thrown outward. Okay, so if you wanna if you wanna gain weight, be fatter, instead of eating a lot of pizza, you keep spinning. You're gonna get shorter, but you're gonna get fatter. Okay. Okay. So let's see. We're given the distance at the initial position, and we're asked to find what? The altitude at the maximum elevation. So let me call that HB, right? That's the first part. And we're also trying to find the position of the satellite when its speed is. So let's go. Where is C? C is where, such that, let's say this is C, such that its speed at C is 35,000 kilometers per hour. Okay, so we're trying to find this distance here, RC. how far am I from the center of the Earth when when my speed is 35 kilometers per hour? Okay? So any suggestions on how we do this? So let's look at the first part. At B, what are the things that we don't know at B? We don't know the altitude, HB, right? What else do we know? Okay, we don't know the velocity at B, right? Which means that we're going to need two equations, right? So what are the two equations that will help us solve this problem? Okay, the first one is conservation of angular momentum, right? And the second one is, whoops, it's not moving along a circle though. If you say it's right, that's only true if it's moving along a circle. That the velocity is what is according to the net force is equal to mass times acceleration normal, right? The fact that we don't know it's not moving along a circle, we don't know the radius of curvature, right? It would be what? Not really. I mean, it's anywhere you are, you can approximate the circle that's tangent to it, but we don't know the radius of curvature of the path. The radius of curvature of the path is not RB. It's not the distance from the center of the Earth. Do you agree? So the RB is HB plus RE, but that's not the radius of the curvature of the path. The radius of curvature is actually smaller, because if you try to set a circle here that's tangent at that point, the radius of the circle is really the rho that we want, and it's not HB plus RE. Yes, the radius of curvature is not equal to the distance from point O because it's not a circle. Yes, that expression is correct. It's true, and however, no, it's still true for not circular motion. However, we don't know what rho is, right? And rho is not necessarily related to HB and RE, the radius of curvature of the path. And the reason for that is because it's not moving along a circle. If it were moving along a circle, the radius of curvature of the path is equal to the radius of the circle. Is that okay? So that's what you suggested is correct. It will give us an additional equation that has V sub B in it, but it will also introduce an additional unknown rho sub B, which is the radius of curvature of the path at point B. Are we okay with that, Lincoln? Okay. You don't sound convinced. Okay, but instead of using that, what do we know is true? Yeah, it's conservation of total mechanical energy, right? Yes, the conservation of total mechanical energy does not depend on the radius of curvature of the path. It only depends on what? The potential energy at that position, which is now dependent on the distance between the Earth and the satellite, as well as the speed, which are the two unknowns that we're interested in. Okay? So conservation of angular momentum says that what? Angular momentum at A, which is what? Distance at A multiplied by the mass multiplied by the speed at A times the sine of the angle between the two, which is 90 degrees. That's the good thing about the closest and the farthest distance must be equal to what? At point B, it's distance at B, right? Mass multiplied by the speed at B, right? And if you want, the m's will cancel. And if you want, we can actually substitute for RA, it's actually the radius of the Earth plus HA multiplied by the speed of A. What's the speed of A? At A is 36,900. Okay, must be equal to the distance at B, which is what? RE plus HB, which we don't know, multiplied by VB. That's going to be our first equation. And the unknowns in this first equation are, of course, HB and VB. And the second equation is conservation of total mechanical energy, saying that since the only working force here is the force of gravitation, and it's it's conservative, we can say that the total mechanical energy, kinetic and potential at A, equals kinetic and potential at B. Okay? Kinetic energy at A is 1/2 mass multiplied by the given speed at A squared, right? What's the potential energy at A? Does anyone remember expression for potential energy for gravitation? It's not mgh. It's only mgh if g is a constant, right? Your distance from the Earth is not changing dramatically, right? So what's the expression for potential energy for gravitation? It's what? Big G. It's negative, right? Big G. Okay. Mass of the Earth, right? Multiplied by mass of the particle divided by distance between the two. Yes. So this is like an integral of the force. The force is what? G_m_m over r squared, right? And we know that energy is, or work is, the integral of the force. That's why instead of becoming over r squared, it becomes over r, and there's a negative in the front. Okay? Why is it negative? Because we derived that before. Gravitation. I think it's the third one. I thought we had gravitation derived last time, didn't we? Oh yeah, right here. Okay, here's potential energy due to gravity. Okay? And there's a minus sign in the front. So let's see. Okay, so must be equal to, on the right side, what will be our terms? 1/2 m of the satellite v sub b squared plus potential energy at B would be, well, minus, don't forget, G, mass of the Earth, m divided by RB. Of course, RA is something that we know. RA is what? It's equal to RE plus 500, whereas RB is what? RE plus HB. As you can see, this equation here I'm going to call equation 2, also has the unknowns VB and HB. Oh, hi. Do you want to take this? Oh, I guess I won't have time today. Is that okay? Okay, I already printed what I needed. Okay. Thank you. I'll take care of it here. Okay, thank you. Okay. So we just need to solve 1 and 2 simultaneously. For the two unknowns. Okay? Okay? Let's look at part B. The position of the satellite when its speed is 3,500. So at C, so problem B, okay, at point C, okay, there are two things that we don't know, right? So we're trying to find what? Point C, right? At point C, we are given what? We are given the speed at C is how much? 35,000 kilometers per hour. But what don't we know at point C? Of course, we don't know how far it is, right? RC is unknown. What else don't we know? The what? So we don't know where this point is, But not only don't we know where that point is, what do we know about C? What's given about C? We know the speed, right? Although we know the speed, we don't know what direction it's going, right? So this angle here, P, is unknown. Yes, unlike here at point B, at the farthest point, okay, we know that the P was 90 degrees, right? Because it's perpendicular to R. Here, at a position along the path that is between A and B, okay, C is not 90 degrees, and we don't know what that angle is. Okay? So we still have two unknowns, and worry not, because what? We have two equations. And the two equations again are conservation of angular momentum. Okay, what would the conservation of angular momentum tell us? That the momentum at point C, which would be distance RC multiplied by the mass, multiplied by what? The speed at C times the sine of the angle at C, right? Because this time R and B are no longer perpendicular to each other, and we know that the cross product in magnitude is magnitude of the first vector times magnitude of the second times the angle between the two vectors must be equal to, what's the initial value of this angular momentum? It's RA and dA, right? And the initial was at 90 degrees. Okay, so this will be our first equation. And the second equation is going to come from conservation of total mechanical energy again, right? Saying that at the final position, PC plus VC, potential energy, not as opposed to velocity, must be equal to initial kinetic energy at A plus potential energy at A. So at C, we have 1/2 mass V sub C squared would be our kinetic energy. What's our potential energy at C? It's a minus again, right? Keep forgetting that potential energy due to gravitation is minus. G times mass of the Earth times mass of the satellite divided by R sub C, no squared, right? Because this is the energy rather than the force, must be equal to initial kinetic energy at A is 1/2 mass times the given speed at A squared minus GMEM over RA. What are the unknowns here? Okay, so the only unknown is really RC, right? And once we find RC, right, we can substitute that RC into this RC in order to find C. Okay? So the only thing new about this problem is not only do we know that angular momentum is conserved because it's in central force motion, but since that force also happens to be a conservative force, the total mechanical energy is also conserved. Okay? And that finishes up work energy, and we are now ready to do impulse momentum, which I think tends to be among the three kinetic principles. What are the kinetic principles? There's three. First one is Newton's second law, right? FVD equals CFG, right? Okay, the second one is what? Work energy. And the third one, of course, is the impulse momentum. Okay? Among the three, the third one tends to be the least favorite among students. The second one tends to be the favorite because it's a scalar quantity, right? Now, how does impulse momentum compare to Newton's second law or work energy? Here we're trying to relate the forces with which kinematic variables? Which kinematic variables are involved in impulse momentum? How do you get momentum? Okay, so you're going to need the velocity. How do you get impulse? How do you get impulse? It involves time. Impulse is really just what? The effect of a force over time. Right? In the same way that work of a force is the effect of a force over a displacement. Okay? So impulse momentum principle. So the principle of impulse momentum derivation, it says. So we can start with what? Newton's second law of motion. Okay, if you like this class, you can thank Newton. Everything we have here is from him. If you don't, you can you can curse him. Okay, Newton's second law. What was his original formulation? That the net force, right, is equal to mass times acceleration, or really it's really the derivative with respect to time of the linear momentum, right? That's how we really expressed it. That's the more general form. That is also true even if the mass is not constant. Okay? So in that case, if we treat this as a separable differential equation, we separate dt and v, so we can interpret v as our dependent variable and p as our independent variable. So we integrate, right, from initial velocity to final velocity, okay, from some initial time to some final time, okay. And I think you're okay if I do this. I will sum forces, I'll integrate first, right, before summing. I think you were okay with that last time, right? Because we said that integration is really just another kind of summation, and according to algebra, what? Addition is a commutative property, right? I can change the order of the addition. Of course, physically now, this is slightly different from what we have. The right side, what's going to happen? Integral of VMV would be what? MV evaluated from the final minus MV evaluated the initial. Okay? This is what we call the impulse momentum principle, right? And what is this quantity here? Integral of any force from T1 to T2 dt. That's what we call the impulse of a force. Force F, okay, during the time from T1 to T2. So it's really just the effect of the force applied over time. So with respect to the impulse, okay, it doesn't really matter how much the object moves. It could be that the object didn't move at all, right? So that the work done is zero. As long as you keep applying that force over time, that force will have an impulse. Yes? With respect to V. Oh, because it's like this. It's integral of m dv. Right? Yes? If n is a constant, right? Integral of dv is just v. It's not v squared. Okay? Okay. But I think I told you before that I have a preferred form of this. Instead of saying this, what does this say? The summation of all the impulses of all of the external forces, okay, is equal to the change in the linear momentum. Okay, I like rewriting it in the form what? mv1 plus the summation of all of the impulses during the time interval from T1 to T2 is equal to mv2. I like this form, which is actually not exactly the same as this form, okay, because this one sort of follows the events chronologically. Do you understand what I mean by that? So if you look at this as a story, okay, I have an object of mass m with an initial velocity v1, and then I have a system of forces, okay, that I apply over time. So what happens is that as a result of the application of the forces, the particle will emerge with a new maybe different final linear momentum MV2. So it kind of follows what happens chronologically. I have an object that's just minding its own business with a certain initial velocity, and then all these forces were applied over time, and because of that, the result is a new linear momentum. Okay? The tricky part here is really just the evaluation of the linear impulse, because it makes it kind of scary, because number one, it's an integration, and number two, it's also a vector quantity. So you're integrating a vector. No, don't worry, because you're only integrating it with respect to time, right? And the easiest way to integrate a vector with respect to time is to just integrate the x component, y component, or z component, if you know all of those three in terms of t. Okay, so what is the interpretation of this linear impulse of a force? If we assume that the force can be expressed in terms of its three components, one along I, one along j, and one along k, okay, so and substitute it there. Take note that the I is a constant, so we can take it out of the integral, right? So we just left with the components along I, j, k, respectively equal to the integral of the x component of the force with respect to time, and so on and so forth, right? So we know how fx, fy, and fz vary with respect to time. We can just do the integration separately. Okay? So the components are really just equal to, a graphical interpretation of this thing is what? If I have a graph of, with respect to time, of f of x, right, as a function of time, right, we know from Calc 1 or maybe Calc 2 that the integral of any function, okay, dependent variable with respect to the independent variable, right, from t1 to t2 is simply just the area under the curve, right? So sometimes you have a graph showing each of the three components, fx, fy, and fz. So the impulse of a force is really, over time from t1 to t2, is really just numerically equal to the area under the graph. In terms of dimensions, okay, dimensions of impulse would be force times time, right? Which should be equivalent to what? Mass times velocity, right? Because if you look at our impulse momentum principle, right, this has got to have same units as this in order for me to add them, right? I cannot add two things that are of different units. So the units of impulse should be exactly the same as the units of linear momentum, right? But it's more common to use Newton second, okay, as our, right, unit for impulse, which of course is numerically equal to units of mass times velocity also. Okay? So, just like Newton's second law, which is a vector principle, okay, impulse momentum principle is also a vector principle, right? This is a vector, as opposed to work energy scalar, right? Because work is a scalar quantity, kinetic energy is a scalar quantity. On the other hand, linear momentum is vector, impulse of a force is a vector, okay? And being nice mechanics teachers that we are, we kind of don't trust that students will be able to apply a vector equation effectively without some help, okay? So just like we invented, or somebody else, I didn't, they invented the free body diagram. Really, the free body diagram is just a way for you to, what, more effectively apply the summation of forces equals something equation. That's the only reason why it's invented, to help facilitate the application of summing of forces. The same thing, okay, since the impulse momentum diagram is the impulse momentum principle is a vector quantity, okay, we're going to help you. So this is your friend, by introducing the impulse momentum diagram, which is really just a graphical representation of the impulse momentum. Again, why do we use this? Just to help you what? Apply the vector equation. Okay? So when you're applying the impulse momentum principle, you may not have done this in physics. What I want you to do is draw the impulse momentum diagram first before you write down the equation. So it's basically a graphical representation of the equation, right? Here's the initial momentum of the particle, and here's the summation of all of the external impulses. The external impulses will just be what? The integral of all of the internal forces over time. Okay? And here, all the F's are external only. You don't have to worry about internal forces. Why is that? Because they cancel out, right? They always come in pairs, right? The force exerted by 1 on 2 is the same as magnitude in the opposite sense as force exerted by 2 on 1, right? So just like free body diagrams, we don't have to show external forces. When we were doing work energy, I kind of warned you that it's not correct to always ignore internal forces. You remember that? The truck in the box, right? Because the complication with respect to work energy is, even though the forces are opposite and of the same magnitude, the work done by these two forces may not cancel each other because the two objects may not move by the same amount. Correct? On the other hand, if we're looking at impulse, okay, the two forces are still of the same magnitude opposite each other, and their impulse are necessarily going to cancel each other. Why? Because the time observed by one body is exactly the same as the time observed by the other. They have the same time. You are integrating them over the same time, whereas for work energy, you may be integrating them over different displacements because the objects might be moving at different displacements. Does that make sense? So it's only a problem if you're looking at work energy. You have to be careful not to automatically neglect or delete your internal forces in your system because their work done may not cancel each other. Okay? But here, if it's internal, you don't have to worry. Why? Because their impulses will be integrated always over the same time interval, because time is time. It doesn't matter where you're looking at A or you're looking at B. If the two forces are opposite, their integral over time will just cancel each other. Okay? And being a vector principle, it may have three components. It can have x, y, z, or it can have normal tangential. It can have what? Radial transverse. It will depend on which one's appropriate. If you have more than one force, okay, we already looked at that. You just sum the impulses of all those forces. Right? So instead of summing the forces first before integrating with respect to time, it's okay to integrate each one with respect to time to find the impulses of each forces before summing them vectorially. Okay, if you have two or more particles, okay, all you have to do is just sum all the momenta, linear momenta of all of the particles, the initial and the final. Okay, and if you have two or more particles in this impulse term, any internal forces between any pairs of the particles you can actually delete from your system because their impulses will cancel as well. If there's no net external force, of course, the impulse will be zero, right? If there's no net force, the net impulse will be zero also, and therefore we come into this special case of conservation of linear momentum, okay? Which is probably the most commonly used example you did in physics, okay? Linear momentum is not always conserved. It's only when the net external impulse is zero that momentum is conserved. Okay, let's look at an example. The initial velocity of the block in position A is given, knowing that the coefficient of friction, so we're given velocity of A is as shown. It's 30 feet per second, and it's along an angle of 10 degrees. Okay, and we're asked to, we also know that the coefficient of kinetic friction is 0.3. So if the problem just gives you kinetic and no static, that means you can be sure that it's moving. Okay, we're asked to find the amount of time, let's call that time delta t, okay, for the block to stop. Okay? Oops, what's this maximum friction? It's a ghost from some other slide. Okay. So it's really straightforward. You can actually solve this using Newton's second law, right? Right? Find the net acceleration, right? And use kinematics to find the time for it to stop, knowing the deceleration, okay? But I want us to use, recognize that this is an impulse momentum problem, right? How do you see impulse momentum written all over this problem? You have velocities, you have initial velocity, and you have final velocity. It stops, right? And you're interested in time. I mean, you can't be clearer than that. You have velocity and time in the problem. It's got to be impulse momentum, okay? And how do we apply impulse momentum principle? I said, what did I say? Huh? Draw a diagram first, right? In this time, you actually have to make 3 diagrams, okay? The first diagram is the initial momentum diagram plus the sum of all of the external impulses in the diagram must be equal to the final momentum. I want you to, when you're doing impulse momentum problems, I want you to have 3 diagrams, okay? In the same way, you probably never did this in physics, right? You just applied mv equals something, okay? This will help you, especially when we get to more complicated systems. In the same way that whenever you do Newton's second law, maybe I should look at the quiz. Did you all draw 2 diagrams? I will be really, really sad if I only see 1 diagram. Oh, look at this. F-frame is 2 diagrams. There's more power to you. Oh, you already have half of the point right there. Okay, so what do I show on the first diagram? So I'm sort of telling the story of the impulse momentum principle. I have the block with its initial momentum, and then suddenly over the period of time from T1 to T2, I have all the forces applied, okay? And then as a result, I have my final momentum, okay? So that's the story of the impulse momentum diagram. So I start with the block, okay, moving with an initial momentum. I don't know what the momentum is, but the mass is, so but it's going to be m times 30, right? To the right, okay? Must be equal to, very careful, it's weird initially. For the impulse diagram, you don't show the force. Okay, look at the diagram. You don't show the forces, you show the integrals of the forces over the time. You show the impulses. So in this case here, what are the forces acting? Of course, I have a weight, which keeps on increasing. Okay, so it's going to be mg, but I don't show mg, right? What do I show? I show the impulse of mg. What's the impulse of mg? It's the integral over the period of time of the force, right? I don't show the force, I show the impulse. But in this case, mg is a constant, so I can actually carry out the integration and just say that the impulse is just what? mg times delta t. Is that okay? So if all the forces are constant, you know, you don't want to be scared by the integral. You can just say it's the force multiplied by the delta t. Okay? Similarly, I also have a normal force here, which I expect to be a constant, right? So I integrate that over time. I don't show the normal force. I show the integral of the normal force over time. Okay? And then, what other forces do I know exist? Friction, right? Since the object is moving to the right, and I'm assuming that the incline is not moving, I'm going to have friction to the left, right? Of how much? It's going to be mu k times n, but I don't show the friction. What do I show? Friction multiplied by delta t. that okay? So the second diagram is not just the force, it's the integral of the force over the time interval. Must be equal to mass times the final velocity. But what's the final velocity? It's 0 because we want it to stop. Okay? So just like we did for free body diagrams equals EFDs before setting up the equations, it might be a good idea to do a what? A Dr. Phil, right? So what are the unknowns here? I don't know what N is, right? And I don't know what delta T is. I actually don't know what M is, but the M's will probably cancel, right? So I have two unknowns, N and delta T. It's just a matter of doing my two equations. So I can select this to be my X prime and select perpendicular to that to be my Y prime. Okay. I probably, okay, so what would I get? Along the X prime direction, what would I get? M times 30, right? Minus, I have two minuses, don't I? Minus 0.3 and delta T, okay, and what else? I also have a component of, excuse me, the mg in the X prime direction. Is that okay, Peter? And it's in the minus also, yes? So minus mg delta T times the sine of 30, right? Must be equal to 0 because there's nothing on the right side. And then along the Y prime direction, what would I get? The first diagram has nothing in the Y prime, so 0. The second diagram actually has the N delta T, right? Minus mg delta T cosine 30 degrees equals 0, right? And the second equation, actually, the delta T will cancel, and I get your, I know you, most of you have guessed that this will be the value of N, right? And I substitute that into this N here, okay, and then I can solve for delta T. Okay? It looks weird initially because most of you would probably solve it using what? First, find the acceleration, right? Right? Some forces X prime, some forces Y prime. You'll find the acceleration. Once you have the acceleration, you use you're going to say, oh, all the forces are constant, therefore my uniformly accelerated motion equations will be valid. V final equals V initial plus A delta T. That's how I find delta T. But I want to show you this, how you can apply, which shouldn't be a surprise because impulse momentum is actually derived from Newton's second law. We simply integrate it over time. Yes? 10 degrees. Sorry. No wonder it's so tiny. I think like 99% of all of the problems we looked at in this class is 30 degrees. So, bye. 10 degrees, 30 degrees, what's the difference? Huge. Okay? Now, there's a... Okay. Oh, is that right, John? Probably he didn't do too well on his quiz and he's going to bribe me when it comes back. Okay. So as I mentioned here, this problem here, I could have solved this without really knowing impulse momentum. I could have, survived using Newton's second law and then kinematics. Okay. Now, the importance of the impulse momentum principle is not really in a problem like this where I could have solved it easily using Newton's second law. It's in a class of problems that can only be solved using impulse momentum, and those problems involve impulsive motion. Okay. What does it mean to be impulsive? To react. Huh? Act on an instant. kind of like you just change your mind suddenly, and no thinking involved, right? So it's kind of related to this, okay? So an impulsive motion is one that involves an impulsive force, a force that is acting on a particle during, here's the impulsive part. You change your mind so in a very, very short impulse. So you have a very, very short interval of time, but the forces are large enough so that there's a significant change in momentum. So generally, what? The integral of the force dt, right, which is some force average times some delta t, is what? Equal to the change in the momentum of the particle, yes? Maybe you want to say it's m times delta v. Do you understand what I have here? I'm just rewriting the impulse momentum diagram, right? Impulse momentum principle. The impulse over time is equal to the change in momentum, which is m times delta v, right? So it's saying that we have impulsive motion if we have at least one force that is so big that even though delta t is very small, right? If F is big, we know from what, Calc 2, big times small is not necessarily small, right? It's what we call indeterminate, right? Remember, infinity times 0 is indeterminate, and we have to apply L'Hopital's rule, right? Indeterminate is really just our way of saying we don't know. It could be big or it could be small, because you have the product of something big times something small could be finite. It's not necessarily small. Right, that's what we're saying. Even though delta t is very small, okay, because the event really happens over a small period of time, okay, it's called an impulsive force because F is so big so that when you multiply the big force by the small time, this thing here is actually not negligible. How do I know that it's not negligible? Well, because the ball actually changed the direction of its motion and therefore the momentum changed. Right? A good example of this is anything that involves collision, right? The actual time of contact between the baseball bat, giant, hey, okay, is what? It's very small, the time of contact. But you know that the direction of the motion of the ball changed, so the momentum actually changed. Therefore, there must be a big force involved, and that's an example of an impulsive force. And there's no way to solve that kind of problem using purely Newton's second law or work energy. So if we have a motion that involves impulsive forces, the only way to do it is impulse momentum. So one approximation we usually apply when there are impulsive forces acting on the system is that we neglect non-impulsive forces. An example is the baseball bat. Okay, so here's the baseball flying. Okay, it was struck with a bat. Okay, we know that, okay, this force here between the baseball bat and the ball is impulsive. It's really big, and that force is the main reason why the motion of the baseball changed. So during that time, small time interval, we're going to neglect the impulse of the weight. We're going to say that the weight is non-impulsive, because this quantity here is going to be so small because the weight is finite. I mean, it's not too heavy, right? Multiplied by delta t, which is very, very small time interval, is approximately equal to 0. Or another way of saying it is the main reason why the ball's motion changed is not because of its weight. It's really because of the impulsive force coming from the bat. Okay, so it's an approximation, but we will apply it most of the time. So when a baseball is struck by a bat, contact occurs over a very short time interval, but the force between them is so large that it's enough to change the momentum, right? Obviously, because it changed from leftward to rightward. And during that time interval, we're going to neglect the effect of the weight. Okay, so non-impulsive forces, which are small, okay, What do we mean by small? Small relative to the big, huge force that is responsible for changing the momentum. Where's the pizza? Nothing? What's that on your... I see tomato sauce. Maybe neglected. Okay? I think we should stop here. So really expect problems on impulse momentum topic to focus mostly on impulsive motion. So I will see you guys in a week. I will be gone. Oh, the office hours also on Sunday. I believe I will be able to make it like 7 o'clock, which is like 9 p.m. in Minnesota. So hopefully we'll be done by then.